welcome everybody. As you can see, we have Eric here, Eric Lescano. He is a postdoc in Zagreb. He did his PhD in Buenos Aires University, and he's visiting us this week. So, and yeah, today we will talk about his work about statistical matter coupled to double geometry. So please, Eric, go ahead.
Thank you very much. Thank you very much for the invitation. It's a real pleasure to be here. Today, I'm going to talk about statistical matter, and I will try to be very clear across the talk, but just to give an idea on mine. When I say statistical matter, I refer to energy momentum tensors that depend on pressure and density of energy. This is for me statistical matter. And we are going to describe Riemannian geometry in the first part of the talk, but then I will try to generalize some these kind of notions. In principle, I will base this talk in the first work you see over there, the 2003. This is the first work we did about this topic. It's a work with Miran, that's a collaborator from Buenos Aires. Last year we continued this work, and now we are trying to make progress in the same line. So I can use this.
Maybe try again with the errors. Yeah.
Thank you. So in the first part, I will give a motivation of why study statistical matter. And I will try to review how to couple this statistical matter to Riemannian geometries. This is relativistic kinetic theory or relativistic hydrodynamics. Then in the second part, I will try to give you some ideas about this double geometry, that it's a generalization of Riemannian geometry, but with connections to string theory related to T-duality. And in the last part, I will try to mix the both first parts and try to couple statistical matter to the double geometry, give you an example about the perfect fluid in the double geometry. And finally, I will give some conclusions and future directions related to current investigation. So we usually couple matter fields considering a variational principle. We have an action, we can define a vacuum Lagrangian and couple matter fields to this Lagrangian. And if we consider the variational principle, we can obtain, for example, in general relativity, the Einstein equation, this equation over here, that it's the equation for the Einstein tensor and for the energy momentum tensor. And we can generalize this idea, for example, to the low energy limit of string theory. And we can define an Einstein equation in the low energy limit of, for example, type 2 string theory or of the bosonic string. And in here, you can consider that these fields are part of the energy momentum tensor or part of the Einstein tensor. This is, I will use this convention, but it's just convention. For me, you can always think that these other fields are part of the energy momentum tensor. You can put these fields in the other side. But this is just for the start. The important point here is that we have these two tensors, the Einstein tensor and the energy momentum tensor. Both tensors are symmetric, and both tensors are divergenceless. These equations over here. And in fact, the question now is, what happens when we couple, for example, a fluid or statistical matter, how we obtain this kind of symmetric and conservation law for statistical matter without using the variational principle? Because we know, for example, from cosmology that we can couple a scalar field or the Lagrangian and try to emulate a relation between a fluid or a perfect fluid and a scalar field. But I would like to compute these kind of relations, the symmetry of the energy momentum tensor and the conservation law, considering relativistic kinetic theory or relativistic hydrodynamics. So here you have an example. When I say statistical matter, I am talking about this, an energy momentum tensor that depends on the energy density and the pressure. This is the case of the perfect fluid. But in here, we are not working with this, only with this. We can consider imperfections, we can consider dissipations, and for example, consider a gas for different proposals. We are always thinking this kind of energy momentum tensors. And I would like to review in a few minutes how to construct the energy momentum tensor from kinetic theory, from in some point kind of first principles in terms of particle physics. So these are 4 steps that I'm going to consider to arrive to the conservation law of the energy momentum tensor. I am thinking in Riemannian geometries, and I will perform these 4 steps. I will define first the phase space for our general relativity theory for a particle in a geometry, in a Riemannian geometry. Then I will study diffeomorphisms on the phase space. Diffeomorphisms, infinitesimal diffeomorphisms are given by the Lie derivative when we talk about ordinary space-time symmetries. But when we go to the phase space, these diffeomorphisms are deformed, I will show. Then I will define a covariant derivative, a notion of covariant derivative on the phase space. And finally, I will construct the Boltzmann equation. If you arrive to the Boltzmann equation, then you have the conservation law, I will show. I will follow these 4 steps because from here, I will go to double geometry. And these 4 steps are useful for that. You can't, if you work, for example, only in general relativity or in supergravity, you can get Boltzmann equation using, for example, analyzing the geodesic equation, because you can define an action for your particle. You understand your particle on a manifold, you define an action for that, the action for the free particle. Then you can compute the equation of motion of that particle, and the equation of motion is related with the geodesic equation. So you can get to the Boltzmann equation in this way. This is a more physical way to obtain the Boltzmann equation, but since I want to go to double field theory and double geometry or things related to a string theory, this other path will not be convenient. That is why I will follow this list. This is a more mathematical procedure to obtain the Boltzmann equation. Any questions so far?
Why is it not convenient?
Why is not convenient? Because in double field theory, all these steps, the action for a particle and computing the equation of motion for the action of the particle in the double geometry is a very obscure, it's not well understood yet. It's not very easy to obtain this. So it's not possible. Perhaps it's possible, but for me, it's very obscure. So I prefer doing the other way in order to obtain the Boltzmann equation. And in fact, perhaps in the future, we can use this construction in order to do the reversal operation and try to understand the action for the free particle in the double geometry. Thank you for the question.
One question, because if you are in string theory, so you would have also, let's say, Ramon sector. I don't remember if the double field theory is constructed for.
Can be included. This kind of fields can be included. The group is not ODD, it's PIN-DT. But in here, in my line, I always use the NS-NS, and I am considering just this sector. Also in double field theory, I will consider only NS-NS.
But then the problem related to the question of Alfonso is that you are using that part from string theory, but then you're willing to couple these to matter that not necessarily comes from string theory. So
this is a very important point, because when I talk about matter, you can think in these 2 ways. You can think that matter is coming from most of the strings, it's matter related to string theory, or you can think that you are coupling matter in the same way you couple matter in cosmology. This is a very important question. And here I will just show a formalism to describe these kind of things. And where this matter came from, it depends on how to apply this kind of formalism. I will be more clear in the next step. Okay, so the first point is define the phase space, and I don't want to be very technical. You need to define a tangent bundle, but in very simple words, we are extending our notion of coordinates, and now our vector and tensor will depend on x coordinates, these coordinates over here, and also momentum coordinates, and they will be independent of each other. I am not going to impose this mass condition, the mass shell condition. This procedure over here doesn't require to impose this condition to work on shell. So in some point, we are going to consider diffeomorphisms, usual diffeomorphisms, but with an extra term. We can erase that.
Maybe
it's possible.
Yeah, it's not better, right?
Well, no, but just for a minute in order to describe the diffeomorphisms, and then we can put.
Yeah.
Okay.
yeah,
So diffeomorphisms in general relativity, these are infinitesimal diffeomorphisms, are given by the Lie derivative, this derivative over here. Here I am considering an arbitrary vector, but this vector depends on both momentum and coordinates. These are the coordinates of the phase space. This is the parameter of diffeomorphisms. The parameter depends only on the coordinates. And this is the new term. We have a new term over here. This is the definition of diffeomorphisms on the phase space, since our vectors in the phase space, vector, tensors, all our objects depends also on P. So we have this term with the derivative of P, the derivative of the momentum. And in principle, the closure of the transformation, if we apply two transformation of this kind, the closure of the transformation, this operation over here, requires a bracket that it's the same that in general relativity. The bracket is not deformed. The lesson we take from the phase space is that the transformations contains an extra term, but the bracket remains the same. This is what happens in relativistic kinetic theory and the mathematical structure of these diffeomorphisms. We have an extra term here. Our vector and tensors depend on both coordinates and momentum. And the bracket remains the same. This bracket is important for the construction of the double field theory.
What is the W in the definition of the Lie derivative?
This is just a density term. It's just a density term. You can define scalars with density or tensors with density.
Okay.
In general, we are not going to use the density term in general relativity in this description I'm giving here, but in double field theory, it's a technical detail, but I can say we have a weight.
And this new term has a geometrical interpretation?
Yes, has a very important geometric interpretations in the sense that you can define, for example, let me think what is the name, you can define, well, I will show. The important point here is that since we have an extra term here, our covariant derivative is different. Let me...
Sorry, this extra term just comes from considering, are you really considering the diffeomorphism in the double space, or is...
In the phase space, you mean? This is general relativity.
Yeah, but do you just consider a space which is twice the size of the region?
Yeah, of course.
And if you just interpret the piece as standard coordinates, you get this.
Exactly. This is.
No, but the vector field is only depends on X, not on X and T.
The vector field can depend on P. Let me give you an example. For example, a scalar here, and a scalar is the distribution function. When you perform, for example, hydrodynamics, we choose a fluid, for example, perfect fluid, and you have a distribution function that is the Maxwell-Boltzmann distribution function, but this is the relativistic case, but you have a distribution function. This distribution function depends both on momentum and coordinate, and it's a scalar with this perspective, inside this perspective. It's a scalar, I don't know if I have the example over here, but the distribution function is a scalar, but it's a scalar that transforms in this way, transformed with the ordinary Lie derivative plus an extra term. This is the covariant way that objects transform. So all your tensors and vectors and scalars depends on both coordinates, momentum and ordinary coordinates. And then when you start from phase space, you can integrate on momentum and define vector and tensor, space-time vector and tensors. For example, the energy momentum tensor is a space-time tensor that will come from the integration of the distribution function that is a space-time scalar. I will be more clear, but this is just to discuss with you.
Why is it so asymmetric with respect to X and T? So only derivative with respect to P or only appear in the extra term?
Derivative with respect to P appear only in the extra term, and this term also, it hasn't got a tensorial structure. It's always the same term, independent of the amount of indices you have on your vector. It's always this extra piece that you need. This is the extra bit you need in order to understand the Boltzmann equation as a covariant equation. I hope I will be more clear.
So I think I have to.
Thank you. So the covariant derivative on the phase space has a deformation, has an extra term because the diffeomorphisms are deformed. And we have the ordinary space-time covariant derivative plus an extra term. The fold operator is known as the Liouville operator in the literature and acts as a covariant derivative on the phase space. And this covariant derivative in here, the D1, this is the covariant derivative for the phase space, satisfies this relation over here because this extra term, when we derive with respect to P, this extra term cancels the term in the spatial part of the covariant derivative. So P, the covariant derivative acting on a momentum is 0, and the first term, the ordinary derivative, is also 0 since this is a basis in terms of the phase space. So we have this condition over here, and we have this operator that is the Liouville operator in the sense that if you take a vector, and if you want that the derivative of a vector acts as a tensor on the phase space, you need to correct the covariant derivative with this extra term. So this is the Liouville operator. And the Liouville operator is very useful to define the Boltzmann equation. I will show you. Can you help me?
No, I think now you can.
Now I can. Thank you. So the Boltzmann equation, as I was saying before, when you pick a fluid or a statistical matter, you are picking a distribution function. For example, for the perfect fluid, this distribution function is the Maxwell-Boltzmann distribution. And the Boltzmann equation in this setup is given by this fully covariant equation. Recall that this P can be put inside the covariant derivative because the covariant derivative here doesn't touch it. So this is the Boltzmann equation. It's like a directional derivative on the phase space. And in fact, this is the Boltzmann equation in equilibrium, because if you are out of equilibrium, in the right hand side, you have collision terms that when you are in equilibrium, these are not present in here. And if we integrate this equation, if we integrate the Boltzmann equation, for example, in this way, this is the Boltzmann equation. I am adding in here one arbitrary object, and I am defining here the volume of the phase space. This is like the volume that is connected with the Liouville theorem. If you integrate in here, you can obtain transfer equations to define this conservation law. You will obtain from here the conservation law of the particle of the particle current, the entropy, the current entropy, and the energy momentum tensor. All these things came from the Boltzmann equation. That was why it was important to reach the Boltzmann equation. If you reach the Boltzmann equation independently of the geometry, if you have a geometry and reach the Boltzmann equation, then you can define the conservation law for your fluid. So, for example, when you pick this object to be constant, you can integrate by parts and considering here the ordinary derivative, and what is inside, all this expression must be understood as integrating our space. And in here, what you are seeing here is the integration of a scalar. F is a scalar in terms of the space of the phase space, but produces a vector, a space-time vector. The integration of the momentum part produces a vector, and this is the current of particles. And when you pick this object to be P, in here you see the definition from kinetic theory of the energy momentum tensor. If you put in here the Maxwell-Boltzmann distribution function and perform integration, you will obtain the well-known energy momentum tensor for the perfect fluid, for example. And if you pick a different distribution function, you will obtain your energy momentum tensor. This is the energy momentum tensor you need to put in the right-hand side of the Einstein equation in order to proceed with the ordinary cosmology, for example, or the dynamical system of equation that you are studying.
So I missed it. Why is the conservation law guaranteed? I mean, this
is guaranteed because it comes from this point. It comes from this. If you pick this object, this is 0 because this is the Boltzmann equation. This has to be 0, and you are integrating over all your phase space.
Yeah, okay.
From here, you just need to integrate by parts in order to transform this derivative in the ordinary one. Yeah. This is here. This equation, you are seeing only the integration in P, but all this expression is integrated also on position. The inside has to be 0. And this is just a definition. You will obtain this object, that this object depends only on the coordinates because I am integrating the momentum. So this depends only, this is a space-time vector. This is how you transform a phase-space scalar, F is a phase-space scalar. You transform this into a space-time vector. And the same way you can transform this, if you consider this arbitrary P over here, you can obtain the definition of the energy momentum tensor coming from kinetic theory.
But the zero is once you integrate over X, no?
The zero is one you integrate over X, yes.
So why is this?
If you have a kind of border term or something like that, you can deform this conservation law at some point.
No, what I'm saying, the zero is after you integrate, not before you integrate.
Is yes, the integration over all the space-time integration has to be zero.
Why is the integrand then zero?
If it is not, if it is, I have an integration over here with position, and the whole integration has to be zero.
Yeah.
So the claim is that what is inside this integral, it's zero.
This is what I am asking. Where does that claim come from? How to justify that claim?
I think that if it is not zero, you need to. I don't remember very well.
You come back to the
Yes.
previous slide because I think it's
Yes.
when you do the last step. Of course, if you remove the integration, so the blue part is zero, so you can remove the integration.
Yes.
Right?
Yeah, yes, this is the point. You remain here, this X, because I am trying to recall the technical detail. Because since you have the measure over here, you need to transform this into, into the ordinary one, into the ordinary nabla, the ordinary covariant derivative, and you will obtain a trace of the connection that you have to put in your computation. That's why you put but in principle, from the first point, this is zero. This is also zero. Yeah.
Those G's, those metrics are
the determinant of the metric. Yes, this is general relativity.
One depends on P and one on X, or
No.
This is the same.
This is the determinant of the ordinary metric.
And it's why it's twice there?
And this is the volume from this integration, and this is the volume from this integration in the first space.
Yeah.
The whole thing is the volume of.
What I'm saying is the same square root of minus G twice, or is different?
Yeah. You can just put G. dp dx. Okay. Yeah.
But can you do this computation taking psi to be a more generic tensor of variables in phase space?
Yeah, for sure.
And what do you get?
Yeah. No, I don't know what you get, but you can do the integration.
Yeah, okay. That you can because it's just the Boltzmann equation is zero, but
it depends it depends in what object you put in here, because you have special options in order to obtain, for example, the energy momentum tensor or the entropy. You obtain always conserved quantities.
I wanted to know if you get conservation of higher spin currents, for example, if you can do that.
I don't know that. I don't know. But in principle, I am just focused on this part because I am just trying to reach the energy momentum tensor in order to relate to the Einstein equation. This is my motivation, but I am not sure.
And you said that the Boltzmann equation is related to the equation of motion.
Yeah, the Boltzmann equation is related to the equation of motion of the free particle. If you have a particle on the geometry, then you can go to the momentum, to the phase space, take this geodesic equation, and if you are in the phase space and you grab the equation of motion, you can rewrite it in this way. This is exactly the geodesic equation if you define the phase space. It's exactly the same. Sorry, there's another question. It's a very good moment to continue answering. This is kind of review. This is general relativity. This is well-known things, and then I will try to generalize this, performing the same steps. I would like to perform the same structure.
So then this equation is satisfied for any distribution function, assuming that it obeys the equations of motion.
No, from this perspective, there is no equation of motion because I am not considering any Lagrangian.
You're talking about geodesics.
You can talk about geodesics, but in here with this procedure, you only have particles on the geometry.
This equation is just an assumption, or is always true, or is it a restriction on the F?
this equation is always true. It's always true if you have particles, statistical matter, particles obeying statistics on a geometry, and you define the phase space of that geometry. This equation is always true. It's the Boltzmann equation. It's the way the particles. This equation is the dynamical, the kinematical information about how are the collision of the particles in this geometry. And this is in equilibrium because if your fluid is out of the equilibrium, if you start doing, I don't know, thermodynamics, relativistic thermodynamics or hydrodynamics, then in the right-hand side, you have contributions.
So is this the relativistic version of Liouville equation or not?
Yeah, it's the same as the Liouville equation. Any other question? Okay, so let's go to talk a very few minutes about double geometry, why I would like to generalize the previous things to the double geometry. And the main reason is that if you start with a low energy limit of string theory, if you consider that this low energy limit that I am calling Zagreb is a supergravity, and if you perform a compactification, if you consider that part of your dimensions are compact, particularly in a toroidal manifold, then you obtain this symmetry, this ONN symmetry. Your theory is invariant under this group, this symmetry group. So from here, I would like to motivate the construction of a different geometry, not the Riemannian one, but a geometry that contains information about this symmetry, that we can construct objects that be invariant under this symmetry, and not ONN, because NR is related to compactifications. I would like to just construct invariants under the full dimensions, under the full ODD, that it's also a symmetry of string theory, is an exact symmetry. So the idea of double field theory is to rewrite supergravity in terms of multiplet of this symmetry before compactification. In some point, this ODD turns into a global symmetry, and we need to construct a geometry in order to preserve this symmetry, this symmetry that comes from string theory. And the main abstraction, if we want to do this, the main abstraction is that we need an extra set of coordinates. This is just for space-time. Our space-time, our Riemannian geometry requires a double amount of coordinates. We have the ordinary coordinates. If you want, these are the x that I was using before in my part one. This will be the x's. And now I have these other x's that are new coordinates that I need because the dimension of the group of the symmetry that I want to impose in a global way, it's 2D. So I need to enlarge first the ordinary space. And in fact, since I want to construct the phase space of this, I won't have a double-double because the coordinates will be double. And then when I go to the phase space of this theory, I will have double momentums in the sense that I will have a P for this coordinate and a P tilde for this other coordinate. This is the basic idea. And the basic idea is, again, to define diffeomorphisms. This story is very similar to the previous one. We have a different kind of diffeomorphisms. Now we are not in a phase space, we are in a double space, and we have a diffeomorphism that contains an extra term. This is similar to what happens before. In this case, this is more symmetric, regarding to the question, this is more symmetric. These are diffeomorphisms on the double space. And on the double space, indices are contracted. These indices over here are contracted with the invariant group metric that it's a non-dynamical metric. So in some point, we have two kinds of metrics in here. We have one to contract indices that it's an invariant one, and then we will have the dynamical one, the dynamical metric. So we have two kinds of metrics in here. We have a constraint that is a strong constraint that when you have contraction of derivatives, no matter what kind of field or parameter are on here, this condition is, this constraint forces us to this to be zero. And this is a requirement in order to have closure of the diffeomorphisms transformation. The closure is not given by the same bracket that I showed before. It's not given by the Lie bracket. It's given by the C bracket, that is a different one. But when we go from the double geometry to the ordinary geometry, this bracket turns into the ordinary bracket. So in some point, what we are doing is changing the geometry changing, enlarging the space, changing the homomorphisms, but we have closure if we impose this strong constraint. This will be important because when we construct the phase space of this theory, we will have this strong constraint over here, but for momentum derivatives. We will have an extension of the strong constraint. And from the lessons that we take from the part 1, we want that our phase space contains a deformation of these diffeomorphisms of this Lie derivative, but preserves this bracket. The C bracket must be preserved in order to apply the same philosophy as in general relativity.
Is this a Lie bracket? Or?
No, this is not a Lie bracket. This turns into a Lie bracket when we go from double geometry to ordinary geometry.
So you don't have Jacobi identity?
Jacobi identity is, we don't have a Jacobi identity, no, but it fails up to a trivial parameter. This, in terms of L infinity, this defines, this is not a Lie algebra, but it's an L infinity algebra. So Jacobi identity fails, but fails up to a trivial parameter, so you can define the algebraic structure of this theory. You can define the L infinity, you can define products. I don't know if you are familiar with this.
No, I mean, Jacobi identity usually is of associativity.
Well, but since Jacobi identity is mixed up to a trivial parameter, associativity is still remain. It's a very technical detail, but it's okay with that.
But
so,
if you impose the strong constraint, don't you have Jacobi?
If you impose a strong strong constraint is this equation over here, and solving the strong constraint is killing half of the coordinates. If
you assume that you're always on the strong constraint, isn't Jacobi satisfied?
No. The Jacobiator is not null. The Jacobiator of these diffeomorphisms are not null. But if you apply the generalized Lie derivative using the Jacobiator, this parameter, this gives always 0. This is the point of the open theory. It's a very rich and nice mathematical structure. And in terms of this L infinity, many things can be described in a nicely way. It's okay? It's another question, sorry. So the fundamental fields here, we have an invariant metric to contract indices, but our two fields, our dynamical fields, are a generalized metric that contains a symmetric metric, and a B field contains at the same time the metric and the antisymmetric tensor, and also a generalized dilaton. These are our two fields, and these indices are the ODD indices that I showed you in the previous slide. So in some point, we need some constraint on this object. I don't want to be very technical, but this metric is an ODD element in order to the degrees of freedom, to have a very good counting of the degrees of freedom. And these fields, I am always thinking that these fields depend only on one of half of the coordinates. So for example, I can solve the strong constraint saying that this object is 0, and I return to ordinary Riemannian geometry. I am not considering that dynamics coming from the dual coordinates. So it's just a rewriting, but in this rewriting, we have manifest ODD global symmetry. So we have an Einstein equation in this kind of geometry. We have a Ricci scalar and a well-defined action principle, but I don't want to talk about that if you don't mind. I prefer focus on the Einstein equation. The Einstein equation is very well understood, and also the conservation law. The conservation law from the Einstein tensor is exactly the same as general relativity. You have Yankee identities. And this equation, this conservation law of the energy momentum tensor is okay if you come from the variational principle, in the sense that you can define a matter Lagrangian and ask this to be invariant under the new diffeomorphisms. But the point in here is try to obtain these relations from when a statistical matter is coupled in this double geometry, considering kinetic theory as before. So I am trying to perform this 4 step that I showed you before. Everything will work very well. Sorry, is there any question? I will just try to combine these two things. The first part that was related to ordinary kinetic theory or relativistic kinetic theory, and the second part that where we define this double geometry. I will try to mix both ingredients now.
Sorry, in the previous slide, if you, just to be clear, if you want to couple here, I don't know, whatever some field.
A scalar field, for example.
Yeah, so you have to first to promote the field to double space.
Yeah.
Yeah. Is that ambiguous or
you can? I cannot write in the blackboard, right? Sure. You can define, for example, it depends on your field. It depends on your field. You can define, for example, something like this. You will obtain the Klein-Gordon equation in the double space. You can do that without problems. You can do, I can continue. You can do the same for Maxwell. Maxwell is a little tricky if you want Chern-Simons, but if you want ordinary Maxwell, you can do it without problem. We can couple. We know how to couple. And of course, as you said before, we have in double field theory the Ramon terms. We have the supersymmetric part, for example, the hydrodynamic string. Matter fields are very well understood, but statistical matter and kinetic theory, it was before this work wasn't part of the literature.
So fermions are.
Yeah. You can define fermions in here. Fermions are really interesting because, for example, if you define quadratic string theory, you can put this is a DFT Gravitino. And in double field theory, this is containing both ordinary Gravitino and Gaussian. You pack both fields in only one. This is a different from this. I can put the line, whatever. This is a different one. In double field theory, you can packet your fields in an ODD invariant way. This theory over here, you will have, for example, for your scalar field in there, this is a ODD scalar, and for the fermions the same. You will have ODD vectors or scalar depending on the geometry.
Yeah, I mean, in the statistical formalism you
wow.
Before.
If you can, you are saying if you can do, for example, statistics as Fermi or Bose-Einstein, this kind of statistics, not only classical. I am talking here only about classical. I am not exploring.
Okay, but we have vector fields.
Yeah, only vector field. This is a very, very interesting question. I don't know in the double space. I don't know. Yeah. The statistics for my field will be always classical. Yeah. Thank you. Okay, so let me go to part 3. Just a minute, I will need to check the time.
It's 20 minutes.
Okay, in 5 minutes I can finish. So the idea is to, again, define the phase space. This is a double phase space. Then we need to construct diffeomorphisms. I write here study diffeomorphisms just because I copy and paste my previous slide, sorry, but we construct these diffeomorphisms. We construct diffeomorphisms over here. We construct a covariant derivative on the double geometry in the double phase space. And finally, we construct the Boltzmann equation. This was our work. First of all, the definition of the phase space works in the same way. We are collecting our coordinates in this way. And now the momentum has this big index, and I have 2 copies, the ordinary momentum and the dual one. And now, again, this is the generalized Lie derivative, the Lie derivative of the double space, and we have an extra term in here. And if you study how to construct this derivative with respect to the Riemannian one, then this proposal we given here is the basic one, is the most, is the first proposal you can think. It's the same way we are generalizing this derivative to the, it works in the same way. It's the first proposal we think. And in fact, if we want that the C bracket gives the closure of this transformation, you are forced to impose a strong constraint for both variables, for X and P. You need a strong constraint. And in fact, one of these terms in here, you have contractions, Q contractions in here. This term vanish using a strong constraint. So you keep only one term in here. This is the only term you have in your new diffeomorphisms in this double phase space. But in principle, the proposal was this one. This was our first proposal. We don't impose strong constraint from the very beginning. We try to construct this in the same way that double field theory was constructed, but we were forced to use the strong constraint in order to obtain closure with the C bracket, with the same bracket as before. Of course, these transformations in the double phase space reduces to the ordinary one. This double phase space construction reduces to the phase space construction in a very nice way.
You can make a question. Typically, when the strong constraint, I always thought, I recall this construction, but typically I think just putting the tilde to 0. But is there something non-trivial arising from different solutions to the strong constraint, for instance?
Yeah. I don't know in here. I don't know in here, but in ordinary double field theory, you can always use chi-duality transformation that rotates all your coordinates, all your ordinary coordinates and your dual coordinates are going to be mixed. And you can obtain very non-geometries and a very rich structure of solutions. This is always the easy thing to arrive to general relativity or Riemannian geometries. For sure. And in here, in this construction, in the phase space of double field theory, we have a new Liouville operator, the DFT version of the Liouville operator that contains an extra term, very similar to the Riemannian part. We have this equation, the derivative of P is 0, and we can use this equation and this other equation in order to construct a fully covariant Boltzmann equation for double field theory. So the Boltzmann equation is like this, but now this distribution function is a generic one because we don't know what is the distribution function. We don't have an example of this. We don't have an example of the distribution function. We know that this is the mathematical structure is in agreement with this equation. This is kind of Boltzmann equation when you have particles in a double geometry instead of the ordinary one, but we don't have yet one example of a distribution function, even for the perfect fluid, that it's the most simple case. But we know that we can perform the same procedure as before, and we can obtain the conservation law for this object. The conservation law for the entropy, for example, I am not describing this part because in general relativity is very well understood, but you need the form of this equation in order to obtain the form of this distribution function in order to obtain the entropy. You need to work this equation a little bit in order to arrive to the conservation law of the entropy. So in double field theory, I cannot do that. But the procedure is exactly the same. Produces the conservation law for a current, for a generalized version of a current, and for a tensor. And this is in agreement with the variational principle because we can start in double field theory with this kind of Lagrangian. We can do the variational principle and we will reach the same equation. We will reach the conservation law in the double geometry. So at some point, this is in agreement. And finally, if we want to talk about the perfect fluid, since we don't know which is this, if I start in general relativity and I pick from Wikipedia, for example, which is the distribution function for the Maxwell-Boltzmann distribution in general relativity, I will obtain this energy momentum tensor. I will obtain the ordinary energy momentum tensor for the perfect fluid. However, if I want to do the same in double field theory, I don't know which is this distribution function, and it's not straightforward, therefore, this is constructed in double field theory because this requires thermodynamics. This requires a very well understanding of the temperature of your particles in the double geometry, and this is still work in progress. So in this work, in here, we give a proposal for the energy momentum tensor in double field theory, and we based our proposal in the sense that if we go from double field theory to a reduced version, we need to obtain the equations of string cosmology, since double field theory contains the symmetry of string theory. So the reduction, our proposal, must be in agreement with the string cosmology equations. This is the way we construct the proposal, and we hope that this proposal could help us to construct the distribution function, or at least have a very well-known distribution function that gives this up to terms that these other terms will still produce string cosmology equations. This is the way we manage to construct the energy momentum tensor. And in fact, for the energy momentum tensor, you need to define the velocity, and the velocity obeys this constraint over here. That is a kind of a strong constraint equation. This acts as derivatives in some point. And we have also a mass condition, kind of UHU equal to -1, in order to define a kind of rest frame. This is understood. And finally, in order to obtain the string cosmology equation, you need that these are the DFT hydrodynamics variable, you just need to parameterize in this way or redefine the variables, understand that you have contributions from the dilaton. But if you do that, you can start from double field theory and get to the string cosmology equations. In particular, I am referring to cosmological ansatz. You can take a cosmological ansatz for your double fields, for your H. Yeah. What is H?
The last term, no, the first equation.
H is the generalized metric. This is the metric that contains the G and the B in general relativity. So these string cosmology equations contains information about the ordinary metric, the B field, the dilaton. It's not only a dilaton gravity, but if you kill V, you have a kind of dilaton gravity over there. But we managed to also include this statistical matter and be in agreement with the statistical matter of string theory. And again, this matter over here can be understood as string theory matter, kind of string gas cosmology or matter related to the modes of string theory, or you can think just coupling and string background to ordinary, just coupling the string background with extra matter fields that perhaps they are not coming from string theory, they are coming from somewhere else. Or they are effectively describing what happens from string theory. All these possibilities are can be studied from this model. So the conclusions of this talk is that I show you how to construct the generalized derivative and the Liouville operator in the phase space of double field theory. We derive the conservation law. We give a proposal for the energy momentum tensor. This was, I hurry a little bit with this last part, but we have this last work, this preprint in our hub that you can read about the construction of this energy momentum tensor and the philosophy in order to give a proposal. And the future direction, the thing that we are currently working is how to construct the distribution function for our perfect fluid. This is important, as I said, for the conservation law of the entropy. With this object under control, we will have the entropy of this setup. Then we can construct, with the entropy, we can construct a fully duality invariant thermodynamics. We will have a kind of first and second principles in the double geometry. And finally, and last but not least, the alpha prime corrections could be important in this setup because we can include alpha prime corrections. We know how to include alpha prime correction in the left-hand side of the Einstein equation from the double geometry, but the question is what happens with the right-hand side. Okay, thank you very much. These are useful references in order to learn this object from the very beginning: relativistic theory, double field theory, string cosmology, or string gas cosmology. I use useful references because I give also my papers. These are the useful ones, the useful references.